Hello and welcome back. So in this video, before we dive into the wonderful world of parsing, Nelson's going to first give you guys an overview of parsing. He's going to be talking about lexical analysis using lexers. He's going to be talking about parsing. We're going to be talking about tree parsing and tree visiting, as well as emitting code performing actions. So there's a few interesting things that are very important to have at least a basic understanding of before we move on into the more specific stuff in regards to parsing. So with that, let me go ahead and hand this on over to Nelson.
Alrighty, so parsing has pretty much been the same for the last, well, I don't know, 40 years or so. People have come up with some really effective patterns for taking text in a language and turning it into something else. And that's really the goal of parsing. So you take, you define a language specification, which, is sort of this nebulous, overview of what constitutes valid code or valid words or sentences within that language, and the result of what should happen when those sentences are encountered by a compiler or interpreter. And that's what we're going to basically be doing, taking structured text and making it do something.
Okay.
So the basic overview of parsing in a very general sense of taking structured text and turning it into something else is right here with these 4 steps. And these 4 steps, again, actually get broken down into sub-steps and so on, but these are the 4 main areas that we're going to be breaking things up on because, well, they make the most sense to break them up like that. The first one is lexing. Lexing is about establishing structure of text. It's about figuring out what particular groups of characters mean in isolation. So if a lexer was to identify numbers that were connected without white space in between them, it'll identify those as a number token as an entire group.
Well, you could also think about lexical analysis in the sense of us reading. When we read, we don't read character by character. We identify words.
Right. And that's what the lexer identifies and turns them into what are called tokens, and those are the words of the language. Then the parser takes that stream of tokens and establishes meaning. So it actually takes all those individual words, looks at them and their relationship to each other, and identifies parts of the grammar or the parts of the language that you are trying to express, and it gives those meaning. The output of a parser isn't necessarily going to be an AST, but in a lot of cases it is. An AST is called an abstract syntax tree. And you can think about an AST like the way that a person might read a sentence is we kind of break things out. We subconsciously identify what is happening. We identify the parts of the sentences of the sentence. We identify what the subject is, what verb is acting on that subject, and so on and so on. And that's kind of what an AST is. It's a meaningful representation through the use of a tree data structure. So it's taking, the parser turns the tokens into a meaningful representation. Then we get into an AST parser. An AST parser can gather, rewrite, or execute tree nodes directly if it wants to. It takes in that meaningful tree and it does something to it. And the output of an AST parser can technically be anything. Again, just like a parser, the output could be anything. But a lot of the times it'll just, rewrite and result in another AST. Finally, the last step is the emitter. The emitter doesn't always exist in all solutions, but it is a very important concept for a lot of different languages. That's going to take your AST and it's going to turn it into another textual or binary format that can then be loaded by a CPU, even if your output was a binary, or it could be assembled by an assembler if the output is assembly, and so on. But I'm going to go ahead and walk through each one of these steps again a little bit more in depth. A lexer is going to the input and output of the lexer is going to look like this for the first language we're putting together. Basically, like we said before, you start off with the just text, just a bunch of text. The computer doesn't really know what it means. We can identify meaning out of it just by looking at it, but obviously a computer needs to be instructed how to identify meaning. And the first step is turning it into these tokens. Now, it's important to know also that whitespace is ignored. This output, I formatted it to correspond with the tokens that this text represents, but in reality, it's actually just a stream of these tokens, a one-dimensional stream of them. And you'll see that, for example, the H1 text is turned into an identifier token. The open curly text is turned into an O curly token. The font size text is turned into an ident token, and so on and so on. And with these, now that we've established the meaning, or not the meaning, but what individual words are, we can then obviously much easier identify the meaning of the words as a whole. It's also important to realize that just because I'm showing the token names of each one of these tokens, they don't actually lose information. So inside of our parser, we will have a data structure called a token that contains both a token type and the text that that token constitutes. So this identifier token, its type will be of ident, but the text inside of it will be of H1.
Its value. And obviously, we can't lose that. Otherwise, the output that you're seeing on the right, if that's all that we had in tokens, that doesn't really have any meaning whatsoever.
Right. But computers computers prefer this sort of format when actually, talking about parsing and stuff.
Sure.
If you were to write a parser without a lexer, yeah, good luck. So now I'm going to go on to parsing. So now we have a tree, we have a stream of tokens, but we need to find out we have to establish the meaning of these tokens. We have to build a piece of this program that can take in these tokens and turn them into sentences in the internal representation of our language. And that's where the AST comes in, the abstract syntax tree. So what you see right now is an example of what an AST could look like if we were selecting or if we were parsing the token stream I just showed you. And you'll notice sometimes I'll use like the tree types like this element selector, and sometimes I'll use their value like font size 20pt, but the same rules apply. Just because this is a node of type element selector, it doesn't actually lose the value of it. It still knows that it's an H1 element selector, but for purposes of demonstration, I didn't want to put all that information in this diagram.
Exactly.
So we start off with a root node, and then that branches off into the different high-level or higher-level groups of sentences that we have in our language, which are rules. We talked about that in the video before this. And then each rule is broken out to selectors and properties. So you see that represented here. So this is the point of an AST is, like I said, is to have a representation of your language that's easier for the computer to work with than just a stream of tokens. And that's what we've done here. We've created something that we can easily write a visitor for that will be able to execute actions depending on what types of nodes that we are encountering. So that brings us to the next step. Again, this now we're starting to get into the optional areas. A parser could technically execute actions.
Yeah, let me ask you this. Are you sure that you said optional earlier? As far as the AST parser and the emitter goes?
I might have said optional.
Okay. But it is optional.
Yeah, the reason I say optional, like I said, this is just a common pattern. You will always have a lexer, you'll always have a parser. But if you have a more advanced language, you'll want to have an AST parser, and optionally emitter if your output is textual or binary. Mm-hmm. So the AST parser basically will just parse the AST, walk through the AST, and do different things to it. It can rewrite the tree, gather information. You can do multiple passes with the same AST parser, or use a different AST parser with multiple steps. You can execute the tree right here if you were writing an interpreted language, or in our case, a style sheet, which is built in memory. And we can pass the tree onto the next step, which is the emitter. Now, an AST parser is very, very important, especially for languages like C#, which requires multiple passes over the source code to fully understand what you're trying to mean. And the reason that is because you can define or you can use methods before they're defined. If you've ever thought about that, you could write a main method and then use methods that you defined underneath the main method.
That's
If you
right.
think about the mechanisms required to make that possible, you'll clearly see that we need multiple passes over the AST in order to gather all of the information that we need to understand the intent of the programmer. Languages like C++ and C do not have this. They do not allow, I mean, they allow forward declarations, of course, but they don't allow implicit forward declarations or circular dependencies between files and so on and so on. That's because the compiler or the parsing step does not repeatedly go over the AST generated. Now, yes, there's a preprocessor, but that's irrelevant in this discussion. So next off is we have the emitter. Emitters are really cool. They're commonly referred to as the back end of a compiler. And what they do is they take the AST and they do something to it. Particularly, they create a text or binary file. So the binary files could be, an executable or a binary data file. I mean, let's say we were writing a language that was used to represent data and not instructions. We could emit directly out into some sort of output format. Or even, more awesome, we can output directly to assembly. We can output into x86, ARM, intermediate language, whatever we want to, depending on what kind of runtime we want to run our executable code against. Even kind of cooler, we can emit to a high-level language, such as C, C++, JavaScript, and C#. Now imagine we did write a language, a scripting language, and we wrote emitters for C, C++, JavaScript, and C#. That would be insanely powerful because now you can use your language using the same compiler, the same AST, the same grammar, on a native environment with outputting into C, C++, a managed environment with outputting to C# or IL, or a web environment using JavaScript. And a lot of recent languages actually do take advantage of that. And it's really cool to see, people writing these cool scripting languages that you can execute both on the server side in on a JVM or CLR, and then also execute on the client side using JavaScript. So it's pretty cool stuff.
Mm-hmm.
So those are the four main sort of steps that you can use to go from text to binaries or other language formats. And again, the last two steps are pretty much optional depending on the complexity of your language. Now, during the course of this series, we are going to look at lexing and parsing by hand initially in our introduction to parsing. Our goal is to build a CSS or CGS parser by hand to sort of show people how recursive descent works, how LLK works, how the specific patterns that have been in place for decades, how those actually work to make parsing pretty straightforward and easy to understand and easy to create your own parsers for. But then we're going to introduce a more powerful tool when we get into Antler. And Antler is a tool that allows us to build lexers, parsers, tree grammars, and emitters, every single step that you see here, using a DSL, domain-specific language defined by Antler. And that DSL allows us to express our grammar in a very, very concise way and have Antler output C# code or Java code or whatever, C code or Python code or Ruby code. Antler is an example of something that uses emitters to allow you to target multiple target languages. But Antler, in our case, Antler will output to C# and create, tens of thousands of lines of parsing code that has robust error recovery and stuff like that. That is kind of a pain to build by hand. So we're going to be using Antler to actually write a scripting language that'll use all the steps you see here in order to take a scripting language and compile it into IL. And then, of course, we can use IL-ASM to assemble that into a fully runnable executable. So basically, we're going to be building a .NET language, kind of like C# or VB.NET or F# or anything like that. And so, yeah, that's
pretty much it for an overview. Awesome. Well, with that, we can go ahead and wrap this video up and get started on the lexer. So thanks a lot, everyone, and we'll catch you in the next video.